Hello students, this is Professor Chulai, and in this video we're going to look at the ideal gas law. As always, you can follow along with our Chapter 9 workbook. By the end of this video, you should be able to identify the mathematical relationship between these various properties of a gas, and also to calculate the properties of a gas under certain conditions. Let's get started. Now, in our previous video, we looked at some simple gas laws that relate two different properties of gases. And they're listed up here. So for Gay-Lussac's law, we have pressure and temperature. For Boyle's law, we have pressure and volume. Charles' law, we have volume and temperature. Avogadro's law, we have volume and number of moles. Now, let's ignore the first one for a second because this is pressure and temperature. And let's look at these three that all relates volume to either pressure, temperature, and number of moles. So volume is proportional 1 over pressure, proportional to temperature, proportional number of moles. And let's see if we can combine those. So let's create some space. Let's work right here. So we talked about how volume is proportional to 1 over pressure for Boyle's law, volume is proportional to temperature for Charles' law, and volume is proportional to number of moles in Avogadro's law. I also mentioned earlier that the proportional symbol just means that the volume is equal to some constant times 1 over p in the first example, and that's how we can change a proportional symbol to an equal sign. Okay, what if we combine all of these into a single equation where we have volume is proportional to temperature from here, multiplied by number of moles for Avogadro's law, and divided by pressure for Boyle's law, right? That means that we could write that volume is equal to, we're changing from a proportional to an equal sign, to some constant, let's call it C, times the temperature, times the number of moles, divided by pressure. And because I don't want divide signs, a division sign in my equation, I'm going to move P to the left-hand side. So we get something like P times V is equal to some constant C times T times N. I'm going to rearrange it a little bit. So P times V is equal to, I'll call this, so we have N for here, right? So I'll call this constant C, I'll call it something else. Let's call it R. And temperature. And so this is how we get the famous PV is equal to nRT ideal gas law equation. We basically take the simple gas laws and then change the constant to this constant R. Now, so that's this equation here, PV is equal to nRT. This is one of those equations that you need to memorize. It comes up a lot. And in fact, if you know this equation, you theoretically don't need to know any of the simple gas laws equations because all of the simple gas laws equation can be found inside of this equation, the ideal gas law. So what is this constant R? The constant R is called the ideal gas constant. And by ideal gas, we just means that molecules are behaving such that they don't really attract each other. We'll talk a little bit more about that towards the end of the chapter. But that constant R could have different units, but in a certain set of units will be 0.08206 liters times atmospheres divided by moles times Kelvin. So a few things to note here. If you're using this constant, volume must be in liters, pressure must be in atmospheres, and temperature must be in kelvins. And well, number of moles must be in moles. So if we're using this ideal gas law equation, we must express volume in liters, pressure in atmosphere, temperature in Kelvin, and moles in number of moles to make this work. Okay, now that you know the equation, you know the constant, you know the PV is equal to nRT equation, try to see if you can tackle these questions on your own. I'll do the first one for you as an example. I'll do number 12 as an example. So number 12, it asks us to calculate the volume. So right away, we know the volume is unknown. By the number of moles, it tells us is 0.845 moles of nitrogen gas at a pressure. So it tells us the pressure, 1.37 atmospheres. And the temperature is 315 Kelvin. Okay, the first thing you should do whenever you have an ideal gas law equation is make sure all of the units are what they should be. Number of moles is in moles, pressure is in atmospheres, temperature is in Kelvin. That's all good. We don't need to do any conversions. So now we can use our PV is equal to nRT equation. We need to solve for V. So let's divide both sides by P, right? So that means that V is equal to N times R times T divided by P. So we just substitute, right? N is 0.845 moles. R is 0.08206, right? It's right up here. And the units are liters times atmospheres divided by moles times Kelvin, right? The units are important. The temperature T is 315 Kelvin, and the pressure P is 1.37 atmospheres. So here's how all of the units cancel out that we talked about. Moles cancel out with moles, atmospheres with atmospheres, Kelvin with Kelvin, and we're left with liters. So the volume will be in liters, which is, well, what we expected. You punch all of these in your calculator, and I believe we come up with 15.9 liters for the volume. All right, so I did that one as an example. Try numbers 13, 14, 15, and 16 on your own, and let's see how you do. Pause the video, please do those, and then you can unpause and we'll go over them. All right, let's look at number 13. It tells us we have a 8.50 liter tire, so that's the volume, 8.50 liters, which is already in liters, so we're good. Number of moles, it tells us is 0.552 moles, right? That's here. The temperature, it tells us, is 305 Kelvin, and it's asking us for the pressure in atmospheres and in PSI. Okay, so let's do one thing at a time. Volume is in liters, number of moles in moles, temperature in Kelvin, that's all good. We start with PV is equal to nRT. We're solving for pressure, so let's put pressure on one side. We divide both sides by V to do that. So pressure is equal to nRT over V. So let's substitute. N is 0.552 moles. R is 0.08206 liters times atmospheres divided by moles times Kelvin. The temperature is 305 Kelvin. And the volume, where's the volume? Volume's right there. It's 8.50 liters. All right, so let's see what we get. Liters cancel out with liters, atmospheres cancel with, nope, atmospheres do not cancel out. Moles cancel with moles, Kelvin cancel with Kelvin. And what we're left with is something in atmospheres. Punch this in our calculator, I get 1.63 atmospheres. So we got the pressure in atmospheres. It also tells us to convert it to PSI. We know that 1.63 atmospheres. From our earlier in the chapter, we learned that 1 atmosphere is 14.7 PSI. So this will come out to be 24.0 PSI. 23 sig figs. Okay, let's look at number 14. Pause the video now, please, if you haven't. Try it by yourself first, and then we'll go over it together. So it's asking us to calculate the number of moles of a gas. So N is the unknown. The volume is 3.24 liters. The total pressure is 24.3 psi, but that should ring a bell. Because we need pressure to be in atmosphere if we're going to use the ideal gas law equation. So let's convert it to atmosphere, because we know that 14.7 psi is 1 atmosphere. So this should come out to 1.65 atmosphere. And then we have temperature at 25 degrees Celsius. Again, we need to convert to Kelvin. So we add 273.15. And so that should come out to 298 Kelvin to the ones place. We do PV is equal to nRT. What are we solving for? We're solving for N. So if I divide by RT on both sides, I get N is equal to PV over RT. So let's substitute. Pressure, 1.65 atmospheres. Volume, 3.24 liters. R, 0.08206 liters times atmospheres divided by moles times Kelvin. And what are we left with? T temperature is 298 kelvins. All right, let's see what cancels out. Atmosphere with atmosphere, liters with liters, Kelvin with Kelvin, and we're left with mole, which is what we want, and is number of moles. So number of moles, we punch these in our calculator, and I get 0.219 moles. All right, let's look at number 15. Again, please pause the video, try it first, and then we'll go over it together. What volume? So they're asking for the volume. Okay, we have 0.556 moles of a gas, 0.556 moles of a gas, occupy a pressure of 715 millimeters of mercury. So the pressure is 715 millimeters of mercury. But again, we need pressure in atmospheres. So let's convert that. We know that 1 atmosphere is 760 millimeters of mercury exactly. So this, I believe, should give me 0.941 atmospheres. Okay. Temperature, 58 degrees Celsius. We know we need to add 273.15 to that. That will give us, let's see, 331 Kelvin to the ones place. So we have P, we have V, we have N, we know R always, and we have T, so we can use our ideal gas law equation. PV is equal to nRT. This time we're solving for V, so we divide both sides by P. So V is equal to nRT over P, and so we just need to substitute. N, we have 0.556, did not mean to erase that, moles. R is 0.8, nope, 0.08. 8206 liters times atmospheres divided by moles times Kelvin. Temperature was 331 Kelvin. And our pressure, we calculated as 0.941 atmospheres. So let's see what cancels out. Moles with moles, Kelvin with Kelvin, atmosphere with atmosphere. We're left with liters, which is all good because we're measuring volume, which is in liters. And according to this, I get 16.0 liters if I punch those numbers in my calculator. And finally, let's look at number 16. Again, please do it on your own, and then we'll work it out together. Okay. The pressure in millimeters of mercury, so we want the pressure in millimeters of mercury, so we'll need to do some conversion there. We have a mass of 0.133 grams. That's different, okay. We know it's helium, so let's put helium there. So that's the mass of helium. We have the volume, 648 liters, and we have the temperature, 32 degrees Celsius, so let's add 273.15. It gives us 305 kelvins. Okay, so for PV is equal to nRT, let's see. We need to find the pressure, so that's okay. We have the volume, so let's give it a check there. We don't know the number of moles. We have R, we have T, so we need number of moles. We have mass. We can find number of moles from mass. So let's do that. So let's clear this up a little bit. Let's find number of moles. We know number of moles would be mass, 0.133 grams, divided by molar mass. Helium has a molar mass of 4.00 grams per mole according to the periodic table. So this will give us how many moles? Let's see, punch that in our calculator. I get 0.0333 moles. Okay, that's all very good, because now we can use our PV is equal to nRT equation. We have everything there except for what we need to find, which is pressure. So let's rewrite divide by V to solve for pressure, which means that pressure will be N times R times T divided by V. N is 0.0333 moles. R is 0.08206 liters times atmospheres divided by moles times Kelvin. Temperature is 305 Kelvin. Divided by the volume was 648 liters. So 648 liters. Let's see what cancels out. Liters with liters, moles with moles, Kelvin with Kelvin. We're left with atmosphere, so our pressure would be 0.00129 atmosphere. But we want the atmosphere in millimeters of mercury. So we know that according to our conversion, 1 atmosphere is 760 millimeters of mercury exactly. If you're not sure of that conversion, you would scroll up towards the beginning of the chapter, and that will give us 0.977 millimeters of mercury. All right, so we've done a lot of examples using the ideal gas law. By now, you should have memorized this equation. PV is equal to nRT. You've probably seen this equation before now. The gas constant R, which you don't need to memorize, is this. It's in liters, atmospheres, moles, and kelvins. So that means our volume in PV is equal to nRT must always be in liters. Our pressure must always be in atmospheres. Our temperature must always be in Kelvin. And from there on, it's just making sure our units are in the right, we have the right units. And we know how to do a little bit of algebra to solve for the one component that we want. So when we do experiments using the ideal gas law, right, we're usually interested in, like, for example, number of moles or temperature of gas. And these experiments are often carried out in lab space, right? And in a lab space, the pressure is pretty much the same regardless of where you do it in the world, right? It's going to be the atmospheric pressure. And oftentimes if it's in a lab space, the temperature is not going to vary very much. And so we want to simplify saying, oh, this is always going to be done at atmospheric pressure. This is always going to be done at whatever temperature the lab room is going to be. By saying that things are done at what we call either standard temperature and pressure, shortened as STP, or normal temperature and pressure, or NTP. And this just helps sharing information between scientists across the world a little bit easier. We don't have to always say exactly what the temperature and pressure is because they're pretty much the same from lab to lab. So when we talk about standard temperature and pressure, it means that we're working at a temperature of about 273.15 Kelvin, which for those of you who figured it out was 0 degrees Celsius, right? It's easy to get that kind of temperature. When we're doing experiments, you just get an ice bath, you're at 0 degrees Celsius. And again, the pressure for most lab spaces would be atmospheric pressure, so it's just 1 atmosphere. Normal temperature and pressure, sometimes people might call this room temperature and pressure, right? The temperature is a comfortable temperature for most rooms, which is about 20 degrees Celsius, right? Or if you convert that to Kelvin, which is what we need for gas law equations, it's about 293.15 Kelvin. Pressure again is 1 atmosphere. So you might see this pop up: standard temperature and pressure, STP, normal temperature and pressure, or NTP. This is what temperature that relates to and what pressure that relates to. And it just makes asking questions easier because we don't have to keep telling you what the temperature is, what the pressure is. We know. Okay, so now let's look at this idea of molar volume. Because from PV is equal to nRT, right? We know that we have pressure and temperature that can be standard. So then how much space would 1 mole of gas take up? We know that R is a constant. So how much volume is taken up by 1 mole of gas? That's what the molar volume is, right? It is the volume of 1 mole of an ideal gas using the ideal gas equation. So to do that, we need to solve for the volume of 1 mole. So we set n equals 1 and we solve for V. So V is equal to 1 times R times T divided by P, right? Now, if we're solving this at, let's say, standard temperature and pressure, it means that T would be 273.15 Kelvin and P would be 1 atmosphere. And we know what R is, right? It's 0.08206 liters times atmospheres divided by mole times Kelvin. I should write this a little bit easier so that you can see. R is 0.08206 liters times atmospheres divided by moles times Kelvin. The temperature is, well, we have 1 mole, right? Right, we have 1 mole. It's the volume for 1 mole of gas, so moles will cancel out with moles. Our temperature is 273.15 Kelvin, so Kelvins cancel there, and our pressure is 1 atmosphere, so that atmospheres cancel there. So the volume for 1 mole of gas would be, plug this in our calculator, we get about 22.4 liters. This is the molar volume. It's the volume of 1 mole of gas at standard temperature and pressure. Remember, we had to pick a temperature, we had to pick a pressure. We just used the one that's standard. So this is roughly equal to 22.4 liters at standard temperature and pressure, shortened to STP. Okay, so it doesn't matter what gas it is, right? If it's an ideal, it behaves as an ideal gas. 1 mole of the gas, regardless of what gas it is, will take up about 22.4 liters of volume. You increase the volume, you increase the mole, you increase the volume, you decrease the moles, you decrease the volume. So with that in mind, try to see if you can tackle number 17 on your own. You have ideal gas behavior, right? Which one of these would have the greatest volume? Okay, think about it and let's see what you get. Okay, so we have 1 gram of hydrogen gas, 1 gram of oxygen gas, 1 gram of argon gas. We know that the volume, right? Let's look at the PV is equal to nRT. We know that under standard conditions of pressure and temperature, the volume is directly related to the number of moles. Number of moles go up, volume goes up, number of moles go down, volume goes down. And at standard temperature and pressure, 1 mole of gas should have 22.4 liters. So if we want the greatest volume, we should look for the one with the greatest number of moles, right? And if we look at each of these gas molecules, we find that they have the same mass, right? So number of moles is mass divided by the molar mass. So if mass is the same, then to get the greatest or largest number of moles, we need the smallest molar mass. We need the lightest, if you will, gas. In that case, it's hydrogen. So hydrogen would have the largest volume because it has the largest number of moles, and the moles and the volume are related. All right, that'll bring us to the end of this video. In our next video, we're going to talk about stoichiometry of gases and various properties of gases. So we'll see you then. Bye.